Okay, so ladies and gentlemen, good day all. You are all welcome to my YouTube channel, and today we are going to look at Clausius Clapeyron equation, and the equation is trying to show a relation, or is a relation that describes the phase transition between liquids and a vapor phases of matter. Of course, remember we have different state of matter, so this equation is trying to show the transition or a phase transition between the liquids and a gaseous molecules, so from liquids to the vapor phases of matter. And depending on the form of the equation, it predicts the vapor pressure of a liquid or the heat of vaporization from the vapor pressures at different temperatures. Another use of the equation is predicting whether or not a phase transition will occur under certain conditions. So the Clausius Clapeyron equation is an equation that relates the temperature and a vapor pressure of a liquid. And of course, this equation is ln P is equal to RT all over delta H, that is the vapor pressure of a gas, plus C. And of course, the equation can be rearranged to ln P over P2 is equal to delta H of vapor pressure divided by the universal gas constant, which is R. And we have a bracket where we have 1 all over T2 minus 1 all over T1. So 1 over T2 minus 1 all over T1. And of course, the equation can be rearranged to another form. The equation can be rearranged to another form. It can be ln P2. It can change to ln P2 all over P1 or from bracket plus brackets is equal to minus delta H all over universal gas constant R, then open brackets 1 all over T1 minus 1 all over T2. So the equation can be rearranged as this. So we can either use this equation or this. They are all the same thing. But look at it, the difference is that here is P1 and here is P2. So it's like you take the reciprocal. So it's like the reciprocal of the equation. And here delta H is negative. So the equation predicts the vapor pressure of a solution and the heat of vaporization from vapor pressure at two different temperatures. So this is the equation. This is the two form of the equation. If you are to solve a problem, you can use either this one or this one. So now let's look at an example. Let's look at example. So now we have this question. Now determine the vapor pressure in millimeter mercury of a substance at a temperature of 45 degrees centigrade if its normal boiling point is 115 degrees centigrade and its enthalpy of vaporization is 57.9 Kelvin per mole. And we have P1 is equal to 180 L. So you can decide to use this equation which says ln P1 over ln P2 over P1 is equal to minus delta H over R, then open brackets 1 over T2 minus 1 all over, 1 over T1 minus 1 all over T2. So simply now we can actually drive, or we can now bring out the data. So we have T1 here. The T1 is at a temperature of 45 degrees centigrade. So this is simple. We have to convert it to Kelvin. So from plus 45 degrees centigrade plus 273, we are going to add this, and after we add this, we are going to have the temperature of 318. We have 318 we have 318 Kelvin. And then the second one is the T2, which is the T2 is now equals to, the T2 is now equals to 115 degrees centigrade plus 273. We also convert it to Kelvin. So after we add this and this, then we are now going to have 300. We are now going to have 300. We are now going to have 388 Kelvin. That is for the T2. And of course, our P1 is equals to 180 M. It's equal to 180 M. And of course, remember, 180 M is equivalent to 760 millimeter, 760 millimeter mercury. And of course, we have to convert it to mercury because the questions ask us to determine the vapor pressure in millimeter mercury. So we are going to use this one. So the answer that we are going to get at the end is going to be in millimeter mercury. So therefore, we are now going to use the formula. Of course, the P1, the P2 is unknown. So we are now going to say ln P2, divided by P1 is 760. So we have 760 millimeter mercury, then is equal to, we now have our delta H. So our delta H is 57.9, is 57.9. And of course, from the formula here is negative. So we have negative here, then divided by the R. The R is the universal gas constant. And of course, the R is constant, which is always 8.314. And we now open bracket. We now open the bracket where we have 1 all over T1. So the T1 is 318 minus our T2 is 388. We now close the brackets. So now we now have ln P2 all over 760, and it's now equals to so therefore we now have ln 2, we now have ln P2 all over 760. So after you fresh your calculator, after you fresh your calculator and everything at the end, you are going to have minus 3.951 here. But here, what we want to get is P2. So therefore, we are now going to have P2 all over 760. And of course, remember, if we are taking the link to the other side, it's going to change to exponential. So it's going to be exponential minus 3.951. So therefore, we now have P2 all over 760 all over 760, then is equal to the exponential of minus 3.951 is the same thing as 0.01 0.01 0.0192. 0.0192. Then we now cross multiply, so we now have P2 is equal to 760 times 0.0192. So after you first your calculator and everything here, we are going to get 14.6 millimeter mercury. That is answer, and that is the answer to this question. Okay, so now let's look at another question. So this is another questions. The vapor pressure of a liquid chloroform is 53.1 kilopascal at 24.1 degrees centigrade. And we have 13.3 kilopascal at minus 6.3 degrees centigrade. So what is the heat of vaporization of the chloroform? Given that R is equal to 8.314 joule per mole per Kelvin. So this is simple. We are also going to apply the same formula. We are also going to apply the same formula which says ln we are going to apply the same formula which says ln P2 all over P1 is equal to minus delta H all over R, and open bracket 1 all over T1 minus 1 all over T2. Then we close the bracket. So from here we can also bring out our data. First we have our P1. The P1 here. Our P1. The P1 is equal to 53.1. Then we have our P2. Which is equals to 13.3. Then we have our T1, which is the temperature, is equal to 53, so it's equal to 24.1 degrees centigrade. So we convert it to Kelvin by adding it to 273. Then, so this will give us, if we add this with 273, it will give us 297.1 Kelvin. And then for T2, it is going to be minus 6.3 degree centigrade plus 273. and this will give us 266.7 Kelvin. So now we are going to substitute this, and of course we have our R universal gas constant. We have our R universal gas constant as 8.314. So therefore now we are going to substitute all the values. So the P2 is 13.3. Then our P1 is 53.1 is equal to minus delta H, which is our unknown, divided by R, which is 8.314. And we now open brackets, 1 divided by our T1. Our T1 is 297.1 minus, here is 7, then minus 1 all over 266.1. Then we close the brackets. And of course here we have lin. We have lin outside the brackets. So the next thing now that we are going to do is we are now going to say 13.3 divided by 53.1. So what are we going to get? This divided by this will give us ln 0.25, then 0.25, and we close the bracket. Then we now have equals to minus delta H all over 8.314, then times, after you now say you take this divided by this minus this divided by this, we are now going to have minus 3.837 times 10 raised to the power of minus 4. So now ln 0.25 will give us minus 1.3863. Then if we now cross multiply with this, we now have minus 8.314. It's now equals to minus delta H. And of course we can divide this through the equation. So now we have divided by minus 3.837 times 10 raised to the power of minus 4. So after we now, this of course will now take care of this. So this times this divided by this, we're now going to have 1.1. We have 1906 kilojoule per mole. Kilojoule per mole. And of course here is negative, is minus. So the minus will now come this. So we have minus 1906 kilojoule per mole. And of course this is the answer for question B. So for question 2. So ladies and gentlemen, if you have any questions, you can ask on the comment section. Thank you for listening, and if this is the first time you are coming to my YouTube channel, please subscribe. Thank you.